Oh, welcome everyone, and thank you for joining me today. I am especially excited about today's lesson because we are going to explore one of my favorite topics in polynomial functions, the remainder theorem. And I hope this becomes your favorite too. Rather than just jumping straight into the theorem itself, we are going to begin with a short investigation. And if this investigation is important because it will help us discover not only what the remainder theorem is about, but also why it works. More importantly, it will help us develop mathematical thinking behind the theorem. And when we understand the reasoning instead of simply memorizing a rule, you'll be much better prepared to solve unfamiliar problems with confidence. Let's take a look at the investigation. Notice that in every example, the dividend is the same polynomial x cubed plus 4x squared plus x minus 6. The only thing that changes is the divisor. We'll divide this polynomial by several different linear divisors using synthetic division, and for each one, we'll record the remainder. As we work through these examples, I want you to look for a pattern. Once we have discovered that pattern, we'll use it to develop one of the most useful theorems in polynomial functions. So, let's get started. We'll divide x cubed plus 4x squared plus x minus 6 by x minus 2, and we'll begin by listing the coefficients of the dividend, which are 1, 4, 1, and negative 6. Let's draw our half rectangle right here and identify the value of b. As you can see here, we are subtracting number 2, which makes the value of b equal to 2. So we'll record that in the chart and we'll put it in the division here. Now, because we will be dividing the same polynomial, we're going to set up these divisions in the rest of the investigation. So let's begin with the first division. We're bringing down number 1. So this will be a nice, fun, quick practice of polynomial division, like grill and drill type. So we'll multiply 1 by 2 and we get 2. 4 plus 2 is 6. 6 times 2 is 12. 12 plus 1 is 13. 13 times 2 is 26. Negative 26 plus negative 6 plus 26 is 20. So we're going to say that the last number here in the division will represent the remainder. So the remainder will be 20. So next we're dividing by x plus 2, which means that the value of b is negative 2. So x minus negative 2. So we'll write negative 2 here, the value of b negative 2, start the division, bring 1 down. And again, 1 times negative 2, negative 2. Add. 4 plus negative 2 is 2. Multiply 2 by negative 2 is negative 4. Add again, negative 3. Negative 3 times negative 2 is positive 6. Add again, we get a remainder of 0. So we'll write that down. Next. This time we have x minus 1. So the value of b is 1 because that's a number subtracted from x. So b is 1. Start the division. Bring 1 down. 1 times 1, 1. 4 plus 1, 5. 5 times 1, 5. Add again. 1 plus 5, 6. 6 times 1, 6. Add again. We get a remainder of 0. So we'll record the remainder equal to 0. Next. This time we have x plus 1, which means that we must have subtracted a negative 1. So the value of b is negative 1. Start the division. So bring 1 down. 1 times negative 1, negative 1. Add positive 3. 3 times negative 1, negative 3. Add again. 1 plus negative 3, negative 2. Negative 2 times negative 1, positive 2. Add again. Negative 6 plus 4 is negative 4. Next, we're dividing by x minus 3. So the value of b is 3. So we'll write 3 here and record b on the chart. Bring 1 down. 1 times 3 is 3. Add 7. 7 times 3 is 21. Add 22. 22 times 3 is 66. Add again, positive 60. Positive 60 will be the remainder. Next, we're dividing by x plus 3. So that means that the value of b is negative 3. We'll record this and start the division. Bring 1 down. 1 times negative 3 is negative 3. Add. 4 plus negative 3 is 1. 1 times negative 3, negative 3 again. Add. Negative 2. Negative 2 times negative 3 is positive 6. Add again. We get 0. Remainder is 0. Next, we're dividing by x minus 4. So we're subtracting 4 from x, which makes the value of b 4. Start the division again. 1. 1 times 4, 4. 4 plus 4, 8. 8 times 4, 32. 32 plus 1, 33. 33 times 4 is 132. 132 minus 6, 126. 126 is the remainder. Next, we're almost done. So we are dividing by x plus 4. So x minus negative 4. The value of b is negative 4. Record it. Write it in the division. Start dividing. 1. 1 times negative 4, negative 4. 4 plus negative 4, 0. 0 times negative 4, 0. 0 plus 1, 1. 1 times negative 4, negative 4. Negative 6 plus negative 4, negative 10. The remainder is negative 10. Last, x minus 5 is the divisor, so the value of b is 5. Let's record it. Bring 1 down. 1 times 5, 5. Add 9. 9 times 5, 45. Add 46. 46 times 5 equals to 30. To 30 minus 6 to 24. Remainder is to 24. So we performed the division, so what? Well, we found out what the remainders are. And we did that, by following all the step-by-step division. The next thing that we want to do is find the value of f at b. Now remember that f is the name of the numerator here, f of x. So to find f of b means for the first one to find f of positive 2. And in the next division, we have to find f of negative 2. Because b is negative 2. And next we have f of positive 1. Then we have f of negative 1. See, that's our b value, right? Now we have to find f of positive 3. And then we'll find f of negative 3. And then we'll find f of positive 4. And lastly, we'll have, we have 2 more, f of negative 4. And then f of positive 5. So evaluate the functions at the indicated values of b, or x for the function, by substituting these values into the equation. So what we have in this case is, wherever we see x again, b is coming to play. So we'll have 2 to the power of 3 plus 4 times 2 to the power of 2 plus 2 minus 6. So evaluate this. So we have 8 plus 2, 10, minus 6, 4, 4 plus 16, 20. The answer is 20. You probably already see the pattern, what is happening. So in the same way, we're going to find f at negative 2. So we'll have negative 2 power 3 plus 4 times negative 2 squared plus negative 2 minus 6. So I'm going to do this step by step so we can see it best. Negative 8 plus negative 2 squared, 4 plus times 4, 16. Minus 2 minus 8, minus 8. See, negative 8 minus 8, negative 16 plus 16, 0. So we'll say that the value of the function at b equals 0. I know that we probably don't need to go all the way through, and you probably see and recognize the pattern that the remainder from the division by x minus 2 would be equal to the value of a function at 2. Or in general, we're going to say that if we divide a polynomial function f of x by x minus b, then its remainder would be equal to the value of the function at b. We will finish this investigation just for the fun of it. And it is when I perform these grill and drill exercises when I start feeling math as if it is a sport in a way, because with practice we become faster at thinking, and our brain is racing and trying to think harder and make our hands work harder, faster as well. So it is a mental and a physical sport in a way. So we have 1 to the power 3, 4 times 1 squared, plus 1 minus 6. And here we go. We have 0 again. We're not surprised. So negative 1 power 3, 4 times negative 1 squared, minus 1 minus 6. And again, we get negative 4 again. F of 3, we have 3 to the power 3 plus 4 times 3 squared plus 3 minus 6. So I can use a calculator for it. It's going to be a 60. F of negative 3, we're going to say that we have negative 3 power 3, 4 times negative 3 squared plus negative 3 minus 6. That's a 0 as well. So next, 4 power 3 plus 4 times negative 4 squared plus 4 minus 6. And that will be a handsome number, 126. Negative 4 to the power of 3 plus 4 times negative 4 squared plus 4 minus 6. Minus 4 minus 6. Because it's plus negative 4, minus 6. Now you see that this is a negative 64, positive 64. That's a negative 10 right there. And lastly, we have 5 to the power 3, 4 times 5 squared, minus 4 minus 6. And that would be equal to 224. It's a big positive. This is a big number, so is this one a big positive, and that's where we get this from. Now, the pattern that we notice in here is that the remainder in the division is equal to the value of the function at b. So the next thing that we want to look into is the cases when the remainder was equal to 0. So notice that we had 1, 2, 3 cases when the remainder was 0, and that was when dividing by x plus 2, when dividing by x minus 1, and when dividing by x plus 3. Now, what happens when the remainder is 0? So I'm going to bring back the example we did in the first lesson of polynomial division. So remember that if we have number 6 and you divide it by 2, you get the answer of 3 with no remainder. And we said that 6 can be written as 2 times 3. So we say that when the remainder equals 0, the quotient and the divisor are factors of it. So in other words, we're going to say that If the remainder is equal to 0, then x minus b will be a factor, and vice versa. So when x minus b is a factor, then the value of f of b will be equal to 0. And this is how the remainder theorem will soon tie in with the factor theorem. They are connected to each other, and the remainder theorem is at the foundations of factor theorem, and it helps us factor big, long, high-degree polynomial functions efficiently. Now, if a polynomial f of x is divided by x minus b, the remainder equals f of b, and we call it by another name, the integral remainder theorem. This is not the integral that we use in calculus. Integral means in integer form or coming from integers. And that is because b will be an integer, a negative, a positive, or a 0. Now, we will extend this theorem further to divisors of the form ax minus b, where a is different than 1. And we'll say that the remainder in the division, f of x over ax minus b, I want you to guess, is f at the 0 of ax minus b. Just like it is f at the 0 of x minus b, it's exactly the same thing when dividing by ax minus b. So we're going to say f at b over a will be the remainder. So we're going to say that if ax minus b is a factor, this remainder will be 0, or vice versa. If when the remainder is 0, it means that ax minus b is a factor. A more general form of remainder theorem of this case is what we call the rational remainder theorem. Rational because now we're evaluating a function at a x value that is in rational form or fraction. So we'll say that when a polynomial f of x is divided by ax minus b, then the remainder will be f at b over a. Now we're going to start with our first example and excitingly use this new theorem we just learned. So if you were to determine the remainder when dividing by x plus 7, you would normally perform the entire division. Synthetic, long, doesn't matter. But now we have a quicker way of finding the remainder. So we're going to say that if we want the remainder, all we have to do is find the value of this function at b. So this is our function. So the function is f of x equals x cubed plus 7x squared plus 2x plus minus 5. Now, the divisor here is x plus 7, which means that the value of b is negative 7. So we're going to say that the remainder then will be equal to the value of the function at b or value of the function at negative 7. And all we have to do is substitute negative 7 into the equation and evaluate it. So 7 times negative 7 squared plus 2 times negative 7, and then minus 5. So notice that this will end up being a 7 cubed positive, negative 7 cubed. This will be negative. So negative 14 minus 5 is negative 19. So this will be the remainder. The remainder will be negative 19. Simple and easy. Now, in the next example, we'll determine the remainder when we are dividing by 2x plus 1. So this is our f of x, 6x cubed minus 8x squared plus 3x minus 15. The divisor is 2x plus 1. So what we do is we determine the 0 of the divisor, which is at negative 1 over 2. Now this is going to be sort of our b over a value. So that's our b over a. So we'll say that the remainder will equal the value of the function at negative 1 over 2. Let's be consistent with our colors here. So we have 6, negative 1 over 2 to the power 3, minus 8, negative 1 over 2 power 2, plus 3, negative 1 over 2 minus 15. So that would be equal to negative 6 over 8 plus, remember, negative 8 times 1/4, negative 2, plus 3 times negative 1 over 2 minus 3 over 2, and then minus 15. So in a more simplified form here, we'll have negative 3 over 4, minus 2 and minus 15 will make a negative 17, minus 3 over 2, or should we say minus 6 over 4, and we can make this into denominator 4. So we'll have in this case a 4, and then negative 3. Negative 17 times 4 is equal to a negative 68, and then minus 6. So we got a nice interesting number here. So negative 6 minus 3 minus 68. So that will make a negative 77, I think, over 4. Because that is a 9, so yeah. Now, we're going to look at another example. This is different. It requires a little bit of thinking. And what we're given in this case is a polynomial of third degree. We're missing 2 of its coefficients, and we are given the information that when divided by x minus 1, the remainder is 10. So I will highlight this. And when divided by x minus 2, the remainder is 51. So we have to use this information to find the coefficients a and b. So we're going to start off with the first piece of information. So division by x minus 1 will give a remainder of 10. So what does that mean? It means that the value of the function at 1 must be equal to 10. So this is how you would use the first piece of information. Now, next we have when divided by x minus 2, then the remainder will be 51. So what that means is that the value of the function at 2 would equal 51. So let's create the equations based on these two statements. So we have a x cubed. So we'll start with a. Wherever you see x, you replace it by number 1. Minus 1 to the power 2 plus 2 times 1, and then plus b that we don't know. That must be equal to 10. So this would be the remainder of this polynomial at 1, and that is 10. We'll simplify. A minus 1 plus 2 is 1, and plus b equals 10. Oopsie. And then we have a plus b equals 9. In the same way, we are working with the next piece of information here. So we have a times 2 to the power of 3 minus 2 to the power of 2 plus 2 times 2 plus b, which should equal 51. So we have 8a minus 4 plus 4 plus b equals 51. So 8a plus b equals 51. So I'll call these the equations 1 and 2, or a and b, however you want to call them, or pink and blue. That's another option. And I'll put them together. So if a plus b is 9 and 8a plus b is 51, I can subtract these two equations, and by elimination we'll find that a minus 8a, negative 7a, b minus b will be nothing, and 9 minus 51 will be negative 42. So that will make a equal to negative 42 divided by negative 7, or 6. So if a plus b is 9 and a is 6, that will make the value of b equal to 3. So therefore, we're going to say that the coefficients, a and b, are respectively 6 and 3. And this is the end of the remainder theorem lesson. It is, as I mentioned, tied into the factor theorem lesson, and this is what is coming next. So follow for more. And as always, thank you for learning with me, and bye for now.